All right, hello guys, and welcome to another past paper video. We've been looking at the March 2024 papers. You guys have already probably seen the paper 4 video, which is also from March 24. So the next one that we'll be doing now, relevant to A2, that's paper 5 from the March 24 series. So let's get started with this one. So again, with paper 5, I don't really believe this notion that paper 5s could be difficult or easy. They're almost always the same level. I mean, obviously, if somebody has not covered all of the ideas, then they would find a certain paper 5 easy or a certain paper 5 difficult. But otherwise, they all are the same level. So this is really just a formality of just doing the latest paper. So you guys see that there is actually nothing different about this one. So again, this is also a walkthrough video, not really a solution. Just to save time, I have solved it beforehand, and I'll be going over my solution and talking about the different mistakes that you could have made. All right. So this one, question number 1, which is your planning question. 1.1 shows a thin cylindrical metal rod of length L. This is shown. One end of the rod is hit with a hammer. A stationary sound wave is set up within the rod. The rod vibrates at its resonant frequency F. Microphone placed at the other end of the rod detects the sound wave emitted from the rod. The frequency of detected sound is also the same frequency F. A number of rods of different length are available. Just this statement here should give you an idea that L, the length, is what you are changing. It is suggested that F is related to L by this relationship, which is given here. Rho is the density of the metal, E and N are constants. Plan a lab experiment to test the relationship between F and L. And the rest of the stuff is going to be the same points over and over. First off, let's just define the problem. What's the independent, dependent, and control variables? So I can see that independent is L, the length of the rod, which we'll be changing here. So that's independent. F is dependent. That's what we'll measure. And what should be kept constant here? So always remember that one very easy way to get the control variables from an equation is that the variables which are not the primary independent and dependent variables, and what's not the constants which you need to find, what else you see is a control variable. So here I would say that keep rho, which is the density of the metal, this should be constant. So this is my definition of the problem. So vary L and measure F, or you can say this is your independent variable, this is your dependent variable. Never say that I will control this thing. Say that I will keep it constant. Then this is my diagram here. So one end of the rod is struck with a hammer, right? So this end is struck with a hammer. The other end is where I place the microphone. And because I know that from the microphone, the wave which comes, I will also have to extract the frequency. So the next sensible choice is to connect an oscilloscope here, right? And an oscilloscope is good as far as P1s go because you can write a lot of points about the additional detail of an oscilloscope. So this cylinder is clamped here, so this will avoid it basically moving when it's struck with the hammer. And yeah, this is what it is. Always do make sure that your diagram is really well labeled. Some people also have this habit of not labeling the things which are already labeled by the examiner. This is not a good habit. A lot of the times, the examiner says that for this diagram, there must be some labels. And a lot of the times, the labels are what the examiner has already labeled. So I've labeled this as my retort stand. This is my clamp. And this is the cylinder. This is the length L. This is where it's struck with the hammer. The other end is where I position the microphone, which is then fed into the oscilloscope, right? So now I talk about the experimental procedure. So after striking one end, the waveform will basically, the sound will be heard on the microphone. And because it's connected to the oscilloscope, the waveform will appear. Now we need the frequency. So regarding additional detail, I can talk about the time base that corresponding to the time base setting, I will multiply that by the horizontal number of boxes in which one wave forms. This is going to be the time period. And then I can just take the reciprocal of this to find the frequency f, right? Any variable that the examiner has not previously defined, please do write it out in words. Because the examiner has talked about f, that is why I've written f here. See that I've not written t in the place of time period. So how I like to do it, and I hope nobody is under this sort of delusion, which is that additional detail marks, just because in a mark scheme it's written near to the end, it doesn't mean that you have to write it at the end. How I like to do it is that I like to keep talking about it as I go on. Also because I tend to forget things, as I'm sure some of you do as well. So it just keeps me in the same flow, and I keep writing the additional detail and keep getting done with those stuff. So this is the experimental procedure. Now about the actual measurement part. So you know that we would have to measure L. We just talked about the calculation for F. And we would also have to find this control variable rho, right? So for L, I just say that you measure this using a meter rule. And I also need the density of this metal from which this is made. So for density, I will now refer to this formula, which is rho equals m over v, right? So I need the mass, I need the volume. Because this is a regular shape, which is a cylinder, I can also talk about finding the volume. So for volume, I also need the area. And for the cross-sectional area, I need the diameter, which you can take using a vernier caliper or a micrometer. Here, because the cylinder looks a bit larger to actually place in a micrometer, so that's why I've written a vernier caliper, right? So with the vernier caliper, you can also say that you should check for zero errors. Also, you do this that because of the diameter, you take it along different positions and then you average. Then I talk about the formula, use the area equals pi d square over 4 to find the cross-sectional area. And then you multiply it by the length L. So let's write the length L because that's what the examiner has previously used to get the volume. And then you measure the mass using a balance, and you use rho equals m over v for density. So this is a lot of the stuff regarding measurements. Now we go on to the graphing part. So the equation is this: 2fl to the power n equals root e over rho. And we have to test the relationship between f and L. So now if we look here, because f is my dependent variable, it's my dependent variable. So I've kept it on one side. This is on the y-axis. And I've made f the subject. So everything else is here. But again, I need to plot it against L, right? So what I do is I keep all of this constant stuff, the half and the root e over rho, on one side, and I write L as this. So L to the negative n. So I take it in the numerator, so the power becomes negative. Now, obviously, to get rid of this n in the power, I would need to take the log. It's up to you whether you want to take the log base 10 or the natural log. Both of these work. I usually do take ln, but just for the sake of diversity, I am taking log base 10 here. So log base 10, so that's log f. And when you take the log of something which is multiplied together, so I can talk about this as the logs of these separate things which are multiplied, the logs would be added. So this is log of this thing, the log of this thing plus the log of this thing. So log of this entire thing minus, because the reason for taking the log is to get the n down from the power. So that becomes minus n log L. So now if I look here, this is what would be on my y-axis. This is what would be there on my x-axis. And if I compare with the straight line equation, so whatever is there with the x is m, and this right here is c, right? So this is my y-intercept, which is log of half root e over p, and my gradient is just negative n. But the work is not done here, because your examiner will always want you to make the subject, make the constant the subject of the equation. So if you say gradient equals to negative n here, you would lose marks. You need to go one step further and make the constant the subject, so n equals negative of the gradient. Then you have the y-intercept, which is equal to all of this. So to find E, I basically take the inverse log, which is really raising it to the power of the base. So 10 to the y-intercept is then this thing. And from here, I just make E the subject. So you can square both of these sides or make E the subject. The impact would be the same. So I send this here. So this becomes 2 times y-intercept. And I also multiply by the rho, and then I square it, right? So yeah, that's what I've done. That's what I've done. So I sent this here first, and then I had root E over rho, which I squared. So that becomes this thing squared, and then I send the rho here. So this multiplies, and using indices rules, you can also simplify this. So the square of 2 is 4, and the square of this thing, because you have a power raised to another power, the powers multiply like this. Like this is basic indices rules. Then you always say this line where you discuss what you plot against what. So log f on your y against log L on the x, and the relationship is valid if a straight line is produced. Since we do have a y-intercept here, obviously we would not say it's passing through the origin. Regarding safety, you can also say that the cylinder could fall when we strike it with the hammer. So you use a sandbox to capture the cylinder in case it falls. And also, just for added accuracy, you should perform the experiment in a quiet room so that the only sound which is observed on the oscilloscope is just from that vibrating cylinder. So this is all of question number 1. Again, I've used all of the space available. Question number 2, a student investigates an electrical circuit. Power supply with negligible internal resistance is connected to 6 resistors, each of resistance Z, and a resistor of resistance R as shown. Current is measured by ammeter I. Experiment is repeated for different values of this resistor R. It is suggested I and R are related by this equation. E is the EMF of the power supply. Part A, a graph is plotted of 1 over I on the y against R on the x. Determine expressions for the gradient and the y-intercept. So from this, I basically extract I out as common, and then I cross multiply. So I have 1 over I equals 3R plus 4Z over E. And then I separate the denominator. So that's 3R over E and 4Z over E. I have to plot a graph of 1 over Y versus R. So again, this is what is my Y here. This is my X. Whatever is here with my X, this is the gradient, and this is the y-intercept, right? So 3 over E is the gradient, 4Z over E is the y-intercept. Next part is filling up the table. So you are given R and I in microamperes, and you are supposed to find 1 over I, and you also have to include the absolute uncertainties. Do take care that I is in microamperes and your 1 over I is just in amperes. So you would have to take care of the micro when doing the 1 over I's. Now, because this is all 3SF, you can take your values to 3SF or to 4SF. Again, the easiest thing to do with plotting is that you don't take it to 1 more than the minimum. You just take it exactly equal to that. That's just going to make your plotting a bit easier. So 1 over 225 micro turns out to be this, 1 over 185 micro turns out to be this, and this is how you get the principal values. For the uncertainties in 1 over I, there are really 2 ways to do this. One way to do this is using like a formula. So the idea is that since this is just 1 over I, so they have the same percentage uncertainty. So 5 over 225, and also because they have the same percentage uncertainty, I can also say they have the same fractional uncertainty. So 5 over 225 would be the fractional uncertainty. I just multiply it by this principal value and get the value here. So for example, if I do this 5 over 225 times 4440, this turns out to be 98.667. But again, absolute uncertainties are always 1SF. So this turns out to be 100. If you guys wanted to do it the other way around, if you wanted to use max min, then in this case, what I would do is that I would make it like this. So 1 over 230 micro, 1 minus 1 over 225 micro. And this would also give us the same answer. So 1 over 230 minus 1 over 225. And this is micro. So divide by 10 to the -6. So this also gives us the same value. If you guys look here. All right, so the camera won't let you see. So yeah, so this is 96.6. Again, it's 100 to SF, right? 100 to 1 SF. So that's how you keep filling up these values, 5 over 185 times this, 5 over 160 times this, and this is how you get all of these absolute uncertainty values. Then you plot a graph of 1 over I on the Y, R in kilo ohms on the X. Again, the nice thing about A2, question number 2, is that the scales are already given for you, so you don't have to think about that. So you have to take all of these values and just plot them here. And you also obviously have to make the error bars. That's what's special about question number 2. So if you look at the scales here, so the scales are already given, right? So you just take these values and you plot them. Let's pick out a value at random, which seems a bit difficult. Maybe this one. So 2.55 on the X, 5410 on the Y. So if I look at my values here, obviously right between 2 and 3 would be 2.5. This is 2.55. So that would be even between these two boxes because this is 2.5, this is 2.6. So 2.55, and this was 5410. So this would be 5250 right in the middle. So 5300, 54, 5300, 5300, 5350, 5400, and 5410 would be slightly above, which is why my value is like this. And for 5410, the absolute uncertainty was plus or minus 100. So 100 in this case corresponds to 2 boxes. So I go 1 and 2 boxes up, and similarly 1 and 2 boxes down. Let's have a look at another value just to clarify how we're doing this. Let's take the last value, 7.8 and 8700. So 7.8 on the x-axis. If you look here, this is 8, so this would be 7.9. This would be 7.8. So the second last line, and my y value is 8700. So 8700, where would this be? So obviously less than 9000. This right here in the middle of 9000 and 8500 would be 8750, and one less than that would make this 8700. Right? So that's how I plot all of this. I've done this before because doing this on the iPad takes a lot of time, while plotting it just is too lengthy. It's actually easier to do this on paper. Now I need to draw a line of best fit, versus acceptable straight line as well. And you have to label both the lines. So best fit is this, worst fit is this. So for the line of best fit, again, if I look at my points here, let's see if I can get rid of this for a while, then I'll have this back in. So these are all my points. So again, if I just zoom out so you have a look at the full graph. So ideally, the amount of points I leave above is the amount of points I leave below. So this is below, this is above, this is above, this is above, and yeah. So this is above, and this is also above. This is like almost on the line, so it's not really above. My thinking was that because these two are also relatively close, they kind of offset all of each other out, because this one is slightly further away as compared to this and this. And then this one is approximately on the line, this one is slightly above, this one is slightly below, right? So that's the line of best fit that I get. And then for the line of worst fit, for some reason, I always draw the steepest line. So for the steepest line, it has to pass through the top of the error bar and the bottom of the last error bar and every other error bar in between. But the problem was that when I did have my worst steepest line, when it was going through this, then it was not exactly going through this. So I rotated it around a bit so that it goes through this error bar, right? It has to go through all error bars for this to be acceptable as a worst fit line. Then I have to find the gradients. So for the gradients in P5, it's not really necessary to draw a triangle. I've just labeled the points here. Again, just choose really sharp points. In this one, I really couldn't choose a really sharp point just because of how my line was. The rightmost line vertically, this is 8. And this value, which is here, this is 8880 approximately by sight. That's because this value is 8500. This is 8550. No, just a second. Sorry, this is 8750 right in the middle. So 8800, 8850, and somewhere in the middle. So I've eyeballed that as 8880. Again, with the gradient, you do need to have points which are more than half the length of the line away. So I've taken this one, which is really near to the lower end of the line. So this is 1.123 and exactly 4500. So then I have both of my best fit line points. So I just use change in y over change in x. So if I just zoom out here, so 8880 minus 4500 over 8 minus 1.3. This gives me this value as the gradient. The similar process for the line of worst fit. For the line of worst fit, the points are really easy to see because one of these will obviously be your one of these error bars. So it's the top one, which is 7.8 and 9100. And the nice thing about this is you can also double check using this value because it passed through the top of the error bar. So that's 8700 plus for 400, which is 9100. And the other one, for some reason, I saw another really nice point. So I did not take this error bar. Instead, I took this point right here. Again, this is the false origin, right? This is not a real origin. So 1 and 40, so basically 4100, 4200 is what it exactly is. Again, I have both of my points on the line of worst fit. Again, just using change in y over change in x should give me what I want. So 9100 minus 4200 over the 7.8 minus 1. This is what I've done here. So this is my line of worst fit. You know how I find the uncertainty in the gradient. It's the difference between the gradients of the line of best and worst fit, right? So that's what I got here. Now, some of you guys might also be in the habit of doing this, that you write your absolute uncertainty always to 1SF. That's not wrong. You can do that as well. But for me, what I did here is because everything here was 3SF, I took this as 3SF as well, right? You can take this to 2 or to 3SF. The examiner is not really particular or for that matter clear about this. So this is what I went with. Then I have to do the y-intercept. Again, do keep in mind that since this is a false origin, you cannot get the y-intercept from the lines. You do have to use the formula for this. So rearranging y equals mx plus c, for best fit, this is y minus mx. So one of these points, which was taken above, 8880 and 8. So 8880 was y minus the gradient times x, turns out to be 3648. Exactly the same process for this. I have the gradient. I use these points. 4200 is my y, 1 is my x, and the gradient, plugging all this in, I get this as the worst fit y-intercept. And the difference between the two is going to be the uncertainty here, right? All right, part D1. Using your answers to A, C3, and C4, determine the values of E and Z, include appropriate units. Now, in an earlier part, we wrote down that the gradient is 3 over E, y-intercept is 4Z over E. So if gradient is 3 over E, the constant is 3 over the gradient, which I've already found. So 3 over this value, 654, this is going to be my E value, but I also need to give units. Now, if you think about this, because this value here that I had, 654, when you do this actually, when you do 3 over that 654, this turns out to be something into 10 to the negative 3. And if you look at the units for the gradient, so on the y-axis, we had per amperes. So it's y over x, so that thing is also going to apply to units. So this is per ampere per kilo ohm, right? But because this is per ampere per kilo ohm, then the value of the EMF, the units would basically become kilo ohm ampere, right? Now, because this was 10 to the negative 3 here as well, and there's a kilo in here, both of these will nullify each other out. So you have ohm amperes here. But this is where the entire pretext of the question comes into handy. Because you have ohm ampere now, you were also given this idea that E is the EMF. And if you remember this equation, V equals to IR, so ohm ampere is really just a volt, right? So the units for the answer I got for E are going to be volts. This is the units analysis here. So that's why I struck these out and I wrote volts in the place. So it's 4.59 volts. Similarly for Z, which is the y-intercept times E over 4, just rearranging this equation. So y-intercept 3650, E I just found, divided by 4. So this one turns out to be 4190. Again, the unit of the y-intercept is what you just have on the y-axis, which was per ampere. And because you're multiplying by E, which is volts, so you really have volts per ampere. Again, volts per ampere. If I go back again to the pretext of this question, Z was a resistor, right? So volts per amperes, again, just by the rearrangement of this equation, R equals V over I. This is ohms. So that's what you write as unit. So the value of this one is 4190 ohms, right? So don't write the one in red. For the units, write the ones in blue. Determine the percentage uncertainty in Z. So if you look at the formula here, it's the product of two things divided by a constant. So percentage uncertainty in Z would be percentage uncertainty in the y-intercept plus the percentage uncertainty in E. But because E itself comes from the gradient, so that would also be equal to the percentage uncertainty in the gradient, right? So it's this 170 over 3650. And similarly for the gradient, it's 67 over 654. And because you want to convert these to percentages, you would multiply by 100 here and 100 here. But I've just taken it out as common, just looks neater like this. And I've multiplied by 100 at the end. So that turns out to be 14.9, or to 2SF, I'm writing this as 15%. Part E, the experiment is repeated. Determine the resistance R that gives a value of I of 0.10 milliamperes. For this, you can use either the equation which is given in the question, or you can use that linearized form that you were working with. It's totally up to you. There is no such hard and fast rule of what you must use. What you should use is obviously the values that you did find. So E is 4.59, I is 0.1 milliamperes, R is what I want to find, 4I, and Z is 4190 ohms. So you just solve this, subtract by this entire term here, and then divide by 3 times 0.1 into 10 to the negative 3. The value turns out to be 9713, or to 3SF, this is 9710 ohms. So that's all of this P5. Again, not really all that difficult. I would say that this units analysis was probably slightly tricky here, but overall, yeah, a pretty standard paper. So for your paper fives, do make sure that you do have a really good grip on how the units come about, especially for question 2, drawing the lines of best fit and all the rules which are required to fill up these tables, right? So for example, if I were talking about log tables, that has a really weird rule that whatever is the number of significant figures here, that becomes the number of decimal places here. So let's say if I was calculating log I, because all of this is 3 significant figures, this would all become 3 decimal places when filling out this table. So just make sure you know the rules and the fastest possible ways to find the absolute uncertainties. I generally don't use max min unless it's an absolute compulsion, right? So if you know the rules, I feel like those are more convenient to use. And question number 1, again, when you do the same type of experiments, when you write them out over and over again, you do get a sense of what to write in a certain question, right? So yeah, that's it from my side. For March 2024, we've now done all of the latest papers. So best of luck, guys. All of us are rooting for you. Don't overthink P5 especially. Just make sure that your diagrams are labeled. All of the stuff that you would learn from reading the examiner reports is all there, so that you manage to score well in that paper. All right. So best of luck and see you later. Bye.